Hello, good morning. Myself, MB Guddi, lecturer in EC department. Today I am going to discuss regarding Unit 5 error correcting, error correction and error detection. Contents first one introduction, types of errors, error detection, redundancy, error correction. Introduction. Data can be corrupted during transmission. For reliable communication, error must be detected and corrected. Error detection and correction are implemented either at data link layer or the transport layer of the OSI model. Types of errors. Single bit error, only one bit in the data unit has changed. Burst error, it means that two or more bits in the data unit has changed. Single bit error, the data sent as shown in figure 0 changed to 1 at the receiver point. Then burst error. The sent data is represented, then the received data is represented. Bits corrupted by the burst errors. Error detection. Error detecting code is to include only enough redundancy to allow the receiver to deduce that an error occurred, but not which error, and have it request a retransmission. Error detection uses the concept of redundancy, which means adding extra bits for detecting error at the destination. Redundancy. Instead of repeating the entire data stream, shorter group of bits may be appended to the end of each unit. This technique is called redundancy because the extra bits are redundant to the information. They are discarded as soon as the accuracy of the transmission has been determined. Redundancy. The figure shows data, then generation function, redundancy check, sender, then data and redundancy check at the receiver, checking function, accept and reject. There are basically four types of redundancy check. They are vertically redundancy check, VRC, LRC, longitudinal redundancy check, CRC, cyclically redundancy check. Error detection, vertical redundancy check, longitudinal redundancy check, cyclic redundancy check. Vertically redundancy check, it is also known as parity check. It is least expensive mechanism for error detection. In this technique, the redundant bit called parity bit is appended to every data unit so that the total number of ones in the unit becomes even, including parity bit. Figure shows vertical redundancy check. Checking function is total number of ones even, the data, then even parity generator, then VRC, sender. Vertical redundancy check example is given. Vertical redundancy check. VRC can detect all single bit errors. It can detect burst errors if the total number of errors in each data unit is odd. VRC cannot detect errors where the total number of bits changed is even. Longitudinal redundancy check LRC. In this method, a block of bits is organized in table, rows and columns. Calculate the parity bit for each column and the set of this parity bit is also sending with original data. From the block of parity, we can check the redundancy. Figure shows LRC example, then original data plus LRC. LRC example. Suppose the following block is sent. However, it is hit burst of length 8 and some bits are corrupted. When the receiver checks the LRC, some of the bits are not. Follow even parity's rule and whole block is discarded. The non-matching bits are shown in red, shown in one color. LRC of n bits can easily detect burst error of n bits. Disadvantage: if 2 bits in one data units are damaged and 2 bits in exactly same position in another data unit are also damaged, the LRC check will not detect the error. Cyclic redundancy check. In this method, a sequence of redundant bits called CRC or the CRC remainder is appended to the end of the unit so that the resulting data unit become exactly divisible by a second predetermined binary number. As at its destination, the incoming data unit is divided by the sum number. If at this step there is no remainder, the data unit assumed to be correct and is accepted. Otherwise, it indicates the data unit has been damaged in the transmission and therefore must be rejected. The redundancy bits is used by CRC are derived by the dividing the data unit by a predetermined divisor. The remainder is the CRC. CRC generator and checker. The figure shows sender data 00 n bits, divisor n plus 1 bits, CRC n bits. Then similar way receiver data CRC divisor remainder 0 accept non-zero reject receiver. Then middle data and CRC. Divisor. The divisor is determined according to the algebraic polynomial. The in below example it will be shows x raised to 7 plus x raised to 5 x raised to 2 plus x plus 1. Generation of the divisor form. Polynomial x raised to 7 plus 1. A polynomial should be selected according to the following rule. It should not be divisible by x. It should be divisible by x plus 1. Example, the CRC generated at the receiver end. The CRC checker at the receiver end. Error correction. Error correcting is to include enough redundant information along with each block of data sent to enable the receiver to deduce what the transmitted character must have been. Error correction must be handled in two ways. When an error is discovered, the receiver can have the sender retransmit the entire data unit. Receiver can use error correcting code which automatically corrects certain errors. There are two types of error correcting techniques: a single bit error correction, burst error correction. Error correction can be done with the help of Hamming code. Hamming code. It is a technique developed by R.W. Hamming. Hamming code can be applied to data units of any length and uses the relationship between data and redundancy bits. For example, a 7-bit ASCII code requires 4 redundancy bits that can be added to the end of the data unit or interspersed with the original data bits. These bits are placed in positions 1, 2, 4 and 8. We refer to these bits as R1, R2, R4 and R8. Position of redundancy bits in Hamming code, which will be shown below figure. Redundancy bits. In the Hamming code, each R bits is the PRC bit for one combination of data bits. R1 is the one combination of data bits. R2 is the another combination of data bits, and so on. The combination used to calculate each of the four values for a 7-bit data sequence are as follows. R1 bits 1, 3, 5, 7, 9, 11. R2 bits 2, 3, 6, 7, 10, 11. R4 bits 4, 5, 6, 7. R8 bits 8, 9, 10, 11. Figure shows data 1001101. Adding R1, adding R2, adding R4, adding R8. Then the sent information and received information. Error detection and correction. Following table distinguish between error detection and correction. Error detection, error correction. First one, only errors are detected. Errors are corrected. Second point, less check bits are required for detection, more check bits are required for correction. After detection, correction is essential for or retransmission is required. Retransmission is not required after correction. Example, parity coding. Example, CRC coding. Error control codes. The methods of error detection and correction. First one, parity coding. Parity bits are added to the message at the time of transmission. Depending upon these parity bits, receiver detects errors. Block codes. These codes consist of n number of bits in one block or code word. This code word consists of k message bits and n minus k redundant bits. Such block codes are called NK block codes. Next one, convolutional codes. The coding operation is discrete time convolution of input sequence with the impulse response of the encoder. The convolutional encoder accepts the message bits continuously and generates the encoded sequence continuously. The codes can also be classified as linear or non-linear codes. Linear code. If two code words of the linear code are added by modulo 2 arithmetic, then it produces third code word in the code. This is very important property of the codes since other codes can be obtained by addition of existing code words. Non-linear code. Addition of the linear code words does not necessarily produce third code word. Block codes. Figure shows the functional block diagram of block code. Channel encoder. Input is message block input. Output is code block output. Principle of block coding. For the block of k message bits, n minus k parity bits or check bits are added. Hence the total bits at the output of channel encoder are n. Such codes are called NK block codes. Systematic codes. In the systematic block code, the message bits appear at the beginning of the code word. Thus, as shown in above figure, the message bits appear first, then check bits are transmitted in a block. This type of code is called systematic code. Non-systematic codes In a non-systematic code, it is not possible to identify message bits and check bits. They are mixed in the block. Checksum coding. All the bits in a data block being transmitted are added and the sum is transmitted along with the data. The receiver adds the bits in the received data block and compares the received checksum with the calculated checksum. If there is a difference between received and calculated checksum, error is said to have introduced. Four methods are used to calculate the checksum. First one, single precision. Second one, double precision. Third one, residue checksum and Honeywell checksum. Merits of checksum: most simple technique. Second one, easy to implement since only data blocks are added. Demerits of checksum: it is used only for error detection. Second one, specific error cannot be located. Applications of error control schemes. First one, transmission of data over internet. Second, deep distance communication. Third one, digital satellite broadcasting. Fourth one, storage of digital data. Fifth one, error correcting memory. Figure shows forward error control system. It consists of blocks: input message bits, encoder RC equal to K divided by N, dmin equal to 2T plus 1, transmitter channel R equal to RB divided by RC, which will be given to the what one summer GF equal to N0 by 2, receiver, regenerator, decoder, output message bits. For regenerator, P equal to alpha, detector P equal to BE. Input message bits R equal to RB, which will be given to the encoder input. Forward error correction shows the block diagram of FEC system. The input to the system are message bits at the rate R equal to RB. The encoder takes the block of K message bits and generates a coded message of N bits. Thus the code rate of the encoder becomes RC equal to K divided by N, which is less than 1. The transmitter puts this coded message on some suitable carrier and transmitted over the channel. The bit rate of the channel is R equal to RB divided by RC. At the receiver, transmitted signal is received. The generator reconstructs the coded message. The decoder identifies the message bits and code bits. It then detects and corrects the errors, if any, in the received signal. Thus, in FEC system, no retransmission of the message is done even if errors are detected. The errors are detected and corrected from the code bits only. Figure shows block diagram of ARQ system. It consists of encoder first block, input buffer and controller second block, forward transmission path third block, detector fourth block, output buffer and controller fifth block. Then what output will be destination, the feedback path will be there. Then feedback path, retransmit request. Encoder, it encodes the messages and puts in the buffer. Input buffer and controller, it stores some of the previous transmitted code words. If there is a retransmit request on feedback path, then controller identifies the particular code word from buffer and sends it on the transmission path. Forward transmission path is the channel through which code words are transmitted. It can be a cable, fiber optic cable, or wireless media. Detector. The detector decodes the received signal and looks for errors in it. If no errors are found, then positive acknowledgement ACK is sent to the transmitter on feedback path. The positive acknowledgement is also sent to the output buffer and controller. If detector finds any error received code word, the negative acknowledgement NAK is sent to transmitter on feedback path and output buffer and controller. The negative acknowledgement is actually a retransmit request to the input buffer and controller. Output buffer and controller, it takes code words from the detector and stores temporarily in the buffer. If positive acknowledgement ACK is received, then controller sends the corresponding code word to destination. If negative acknowledgement NAK is received, then controller discards the corresponding code word. Comparison of forward error correction and ARQ. Error detection and correction takes place in FEC, forward error controller. Then only error detection takes place in ARQ, that is automatic repeat request. Second point, data is not retransmitted. Data is retransmitted if errors are found. No feedback path is required. Feedback path is required to send retransmission requests. More number of check bits are required for error correction. Less number of check bits are required for error detection. Code rate is reduced due to more check bits. Code rate is better since check bits are reduced. Transmission rate is higher. Transmission rate is reduced since it has to accommodate a repeat